The Passerini reaction is a chemical reaction involving an isocyanide, a carbonyl, and a carboxylic acid to form alpha-acyl oxyamide. This addition reaction is one of the oldest isocyanide-based multi-component reaction and was first described in 1921 by Mario Passerini in Florence, Italy. It is typically carried out in aprotic solvents but can also be performed in ionic liquids such as water or deep eutectic solvents. The Passerini reaction is often used in combinatorial and medicinal chemistry with recent utility in green chemistry and polymer chemistry. As isocyanides exhibit high functional group tolerance, chemioselectivity, regioselectivity, and stereoselectivity, the Passerini reaction has a wide range of synthetic applications. In order to form this alpha-acyl oxyamide, we need three components: carbonyls, carboxylic acid, and isonitrile. This is known as Passerini reaction. Now, how do we generate this isonitrile? We use Lick's method described in 1859. Silver cyanide, add that with alkyl iodide, and you generate this isonitrile. There are two mechanisms to consider: ionic mechanism used for polar solvents, considered mechanism which is used for aprotic solvents. Now let's look at this carbonyl. It is more reactive than carboxylic acid, so it's going to get protonated first. You're going to generate this good electrophile, and now you have two choices: either use carboxylate or isonitrile as a nucleophile. We know that this isonitrile is negatively charged, it's going to be more nucleophilic, and it's more reactive. So it's going to come in, attack that electrophilic site, which is your carbon, push that electron density towards that oxygen. Now you're going to generate this natrium ion. After that, your carboxylate is going to come, attack this electrophilic site, break that pi bond, and push that electron density towards that nitrogen, forming this immediate intermediate. Now, this is where stuff gets a little bit tricky. So this oxygen is going to nucleophilically attack that carbonyl, which was your from carboxylate, and this oxygen carbon bond is going to break, and all that electron density is going to push towards that nitrogen, making it negative. So this is what you're going to generate. After that, proton transfer will happen, and you generate this alpha-acyl oxyamide. One thing I want to tell you guys is I'm just showing this intermediate, but in reality, this is super fast, so it doesn't even happen. This just happens and it just goes to alpha-acyl oxyamide. But for clarity, I'm going to just show this. Now for considered mechanism, aprotic solvents, you're going to line up your carboxylic acid on the left, your carbonyl on the right, and then your isonitrile is going to be here. So let's start with your isonitrile. So that's going to attack that carbonyl, right? This bond is going to grab that hydrogen, become protonated. The carboxylate is going to be free. It's going to form that bond. And now your carbon-oxygen bond is going to grab that or attack that carbon, pushing the electron density. And you're going to break that pi bond and pushing all your electron density towards that nitrogen. And now you form this immediate intermediate. Similar to this right here. So now this oxygen is going to nucleophilically attack that carbonyl from carboxylate, and that's going to grab that hydrogen. But you know how we saw it here? It's going to be a little bit different. It's going to go through Mump's rearrangement. So after you form this, a nucleophile is going to come in, grab that hydrogen, freeing that oxygen and making that double bond. And now this arrow shows that this bond is going to break, and your nitrogen is going to grab that hydrogen, giving you this alpha-acyl oxyamide. To show the mechanism, most people prefer this ionic mechanism because it is easier to understand.